Hey everyone, welcome back to Learning to Understand Digital Electronics. Today we will be discussing Boolean algebra. When you first hear Boolean algebra, you probably think, oh, this has something to do with binary, the number system. But no, this is more to do with binary, the signal. Boolean algebra is the algebra we use to describe logic gates. So each of these laws we can use to simplify down a big logic gate. So we can be given something like this really long expression describing a logic gate, and we can use these laws to simplify that down to maybe only using a handful of gates, optimizing our system. That's the main case I've seen with like question papers and these sort of things. So this will still follow the same rules as binary, the signal. So when we add two ones together, we won't get 2 or 1, 0 in binary. We'll instead get 1 because a powered state plus a powered state is equal to a powered state. And that's the main thing you have to keep in mind. So with that, let's get into it. By the way, I got this from Integrated Publishing, this picture. I'll make sure to leave the link in the description to the site. So, first of all, A is equal to A. And A inverse or A naught is equal to A naught. Basic stuff. Basically, the variable is equal to the variable. This is something you'll see in normal algebra, so it's not complicated or anything. Just remember that A naught, so if A is 1, then A naught. A is 1, A naught is equal to 0. So it's always the inverse, well, not really inverse, but it's the opposite. And if A is 0, then A naught is 1. Then the next law are the commutative laws, basically saying A times B is equal to B times A, and then A plus B is equal to B plus A. This is very simple stuff. It's not super complicated, so I won't really go into deriving it or anything, but you can just plug in values for A and B, either 1 or 0, and see if it actually lines up, if these two expressions do match, just to practice. But it's basically saying that we can swap the digits in these things around however we want, and they'll still work. Same sort of with the associative laws, that A plus B plus C, I mean A times B times C times C. So this one is going to just be A times B times C. You can also just go and prove that with yourself, plug in a bunch of values, but basically I'm not really going to go and prove it because it's really simple. Like A plus B plus C with these in brackets. And you can just put the brackets wherever you want, and it'll still give the same answer. All this is really saying is you'll find a lot of these same laws in your normal algebra. So this isn't really anything too new. These are basics. Those are your basic laws. Now we're going to get onto the first law that does actually contain a bit of actual Boolean like logic, and that's the idempotent law. Sorry if I did not pronounce it right, I don't think. We never called them this. we just knew what they were. We never actually called them by any name. But a times a is equal to a. Now we can actually look at different examples and see for different values. So if I make a 0, then that'll be 0. That'll give me 0. 0 times 0 is 0. And 1 times 1 is equal to 1. So this holds out. And then a plus a is equal to, because once again, if we have 0 plus 0, we're going to get 0. And if we have 1 plus 1, we're going to get 1. This isn't anything too shocking. You can see since this is a powered state, and it can only be 1 or 0, and since 1 plus 1 does not give us 2, but it gives us 1 because this is a powered state and this is a powered state. So we should get a powered state. So nothing too complicated there. Next, we have the double negative law. We touched upon this a bit in our last video. So a is equal to 1, let's say. Well then, a inverse would be equal to 0. But now if we inverse that a again, we'll just get 1. So therefore, a double inverse is equal to, or a double not, sorry, is equal to a. Nothing too radical there either. Now we're going to get into the complementary law, that a inverse n times a is equal to 0. Well, let's think about this logically. A can only be one of two numbers, 1 or 0. If a is 0, then our answer is immediately 0, since we're multiplying. But now, a inverse has to be the opposite. So if a is 1, then a inverse has to be 0. And then it doesn't matter, but it's going to be 1 here. And then for um, a plus a inverse, well, here we're going to run to the opposite problem, which we find with OR gates. This is an AND gate, this is an OR gate. By the way, I advise you to start thinking of these not just as algebra terms like, oh, it's a times a. This is an AND gate that has input a and input not a. You must try and remember it like that, because that will help you in later sections and help you to actually combine these two things together. So if a is 1 or 0, well, since a is 1, we know we're immediately getting an up of 1 as per an OR gate. And now a naught, well, that's 0. And if that's 0, well, then this has to be 1, and we'll get an up of 1. Now we have the law of union. Oh, sorry, I mean the law of intersection. I skipped that one, which basically says a times 1 is equal to a. That's basic algebra, and you'll also find this throughout. This is basic algebra, and it's not that complicated. It will also work for Boolean. A times 0 is equal to 0. Once again, anything times 0 is 0, so nothing complicated there. And then the law of union, well, a plus 1 is going to give us 1. Same thing, if we have one powered line going to the lamp, it's going to be powered even if a is 0. So nothing complicated there. Then a plus 0 is equal to a. Well, a could either be 1 or a could be 0. So once again, nothing too complicated there. So that gets out most of those are just more foundational laws. I You use them occasionally. Those, yeah, you use them more for understanding things. So they do come into practice a bit, but it's more understanding. Whoa, that's a bit long. Now, these last four are probably the most important. This is the laws that actually help you to simplify things properly. These laws are very, very useful when it comes to simplifying long expressions. Now, De Morgan's theorem, we showed the actual proof for this in our last videos, speaking about AND gates or gates, but it specifically was in the NOR and NAND, showing how they're the opposites. And we proved this. So A plus B inverse. And now if we actually go and look at the proof for this, this is A times B, all not. So these are both under one not sign. So if A is 0 and B is 0, well then we will get an output of 1 because 0 times 0 is 0, and then we invert that, and then we get 1 and 1, which will just give us a value of 1. Now, for the sake of time, I'm just going to say 0, 1, but you can even go and prove it by yourself. But if I swap this 1 to around and I make B 0, it's going to give us the same answer. 0 times 1 is 0, which will give us an output of 1. And then if A will be 1, B will be 0, and that'll give us an output of 1, because 1 plus 0 is 1. And then finally, when we get 1 and 1, well, that's going to give us 1. We're going to invert that, get 0. And then we're going to get 0 and 0, because we're inverting them. And we're going to get, 0. Now, of course, once again, if you want to see a visual proof for it, go and watch the previous video again. Specifically go towards the NAND and NOR gates. So now we have A plus B, all inverted, is equal to A invert, B invert. Remember that this is different to this. There is a gap in the bars. Once here, there is a gap in the bars. This is a solid bar. This is a solid bar. So they are not the same. Be careful with that. Now we'll do a proof again. If A is 0, B is 0. And then I'm just going to speed through this. So I'm going to make this, and this is going to be 1, 1. So 0 plus, so if this is 0 and this is 0, well, that'll be 1, 1, 1, 0, 0, 0. Okay, well, we know that 0 plus 0 gives us 0, so invert that. We know that that'll give us 1, so invert that, gives us 0. 1 plus 1 gives us 1, invert that gives us 0. And then 1 times 1 is 1, anything times 0 is 0, anything times 0 is 0. Pretty simple stuff, but go and practice this a bit because people do mess up here and there. Now, the next ones are the distributive laws. So A times B plus C is equal to A times B plus A times C. Now, this is quite obvious because we're just going to take A into the brackets, and then we're going to get A times B and A times C. What I find is we don't normally end up using the law going this way. We more often use the law going backwards. So actually knowing, taking this case and going to this simplified version is what I find often happens. And then the next one is A plus BC is equal to A plus B. And then A plus C. I mean, A times C. No, sorry. Times A plus C. Well, you see here, this law we're going to need, before we simplify this, we're going to need to know this law of absorption. And this states, first of all, that A times A plus B is equal to A. Well, now this can be simplified into A times A plus AB, which gets A plus AB. Because remember the idempotent law, which is our second case there. Now we're going to go and prove this is equal to A. So if I say A plus AB, so if A is 0, this will be 0, and then B could either be 0, 1, and if A is 1, this is 1, this is 0, 1. So, first of all, A is 0, but now this could still be 1, so we can't just say, oh yeah, it's immediately going to be 1. Well, I mean, it's immediately going to be 0, so 0 plus 0, and then we know anything times 0 is going to be 0, so this is going to be 0 plus 0 is equal to 0, which is equal to A. And then this is 1, and since we're adding, we know this is immediately going to be 1. It doesn't matter if this is 0 or 1, it's going to be 1, because 1 plus anything gives us 1, which is also the value of A. Now, we can take this, and we can see that this will be equal to A times A plus AB plus AC plus BC. Now I'm just going to take that 1A away because A times A is just equal to A. And then using this law, I can cross out these two because they both, we have an A by itself, and then we have an A next to another variable. And this just gives us A plus BC. So nothing too much there, though this took a bit more time to understand. Now, once again, these are very important laws to figure out and to try and understand. And the final law is the law of common identities. So A times A inverse plus B inverse. Well, that's going to equal to AB. And we just going to break up the brackets and say A times A inverse plus AB. And what do we know from the complementary law? That this is equal to 0. And so AB is equal to AB. Pretty simple. And the final thing is A plus A inverse times B is equal to A plus B. Here, yeah, we're going to use the distributive law. We're going to use this law. Treat A inverse as C, let's say. So I'm going to say A plus AB. Well, that's just going to equal A plus inverse A. That's going to equal to times A plus B. And now, once again, we know from the complementary law that this is going to equal to 1, and then 1 times A plus B will just give us A plus B, and there we go. These are by far the most important laws to remember, as they're the ones you'll be work with most often, but also you have to understand the basics. Thank you for your time. I hope you enjoyed this.